Hey everyone! We're surrounded by data all the time, and one of the first things we do to make sense of it is to grab the average. But today, we're going to see why that one little number can sometimes hide the most interesting part of the story.
So let me just ask you this straight up. Can an average ever actually be misleading? I mean, it's just math, right? Well, the answer is a huge yes. And by the time we're done here, you're going to see exactly how. So really get what I mean? Let's imagine we have test scores for 3 different groups of students. Now, they all have one thing in common. The average, or mean score for every single group is exactly 50. But just look at their scores. Would you really say they all performed the same? Not a chance. That's the puzzle we're going to crack. Okay, first up is Group X. This is about as straightforward as it gets. Every single student in this group scored exactly 50. There is 0 variation. So in this case, yeah, the average of 50 tells you the whole story perfectly. Now let's check out Group Y. Here, things are a little different. The scores are 45, 50, and 55. So not identical, but they're all still huddled up pretty tightly around that 50-point average. The mean of 50 still feels like a pretty decent summary of how a typical student did. And then we have Group Z. Oh boy. The average is still 50, but look at the scores. We've got a 5, a 100, and a 45. They are all over the place. Does an average of 50 even hint that one student nearly failed while another one aced the test? Nope, not at all. Here, the average isn't just a little unhelpful, it's actively hiding what's really going on.
So you see the problem. The average by itself just wasn't enough. To understand the real story of these students, we were missing a huge piece of the puzzle. And that missing piece has a name: data dispersion.
Now, dispersion might sound like a fancy technical word, but all it really means is how spread out is the data? Are all the numbers bunched up close together, like in Group Y? Or are they scattered all over the map, like in our wild Group Z? Understanding dispersion tells us how much we can actually trust that average number.
Okay, so how do we actually put a number on this spread? Well, the simplest tool in our toolbox is called the range. It's a fantastic way to get a quick first impression of your data.
A lot of the time, you don't even need to do any math at first. Just look at these 2 sets of test scores. On the left is Test A, and on the right is Test B. You can just see it, right? The scores for Test A are way more scattered. And calculating the range is about as easy as it gets. You just take the highest score and subtract the lowest score. That's it. For Test A, that's 70 minus 45, which gives us a range of 25. For Test B, it's 65 minus 45, a smaller range of 20. So the math just confirmed what our eyes told us. Test A is more spread out. But the range has a really big weakness. It only looks at 2 numbers, the very highest and the very lowest. So what happens if one of those is a crazy outlier? Well, your entire measurement gets thrown off. It's like judging a whole movie based only on the opening and closing credits. You miss the whole plot. So to get a more reliable picture, we need a better tool. And that brings us to the one you've probably heard of, the industry standard for measuring spread, the standard deviation. Now, I know that name sounds a little scary, but the idea behind it is actually super intuitive. All the standard deviation is trying to tell you is this: on average, how far is each individual data point from the center, from the mean? It's way better than the range because it actually looks at every single data point. Okay, let's quickly walk through the logic without getting lost in the math. First, you find the mean, which is 55. Easy. Step 2, you figure out how far each score is from that mean. Step 3 is the tricky part. You square all those distances and then average them out. That number has a special name, the variance. And then finally, to get everything back to normal, you just take the square root of that variance. So after we run our student grades through that whole process, we get this number, 5.228. So what in the world does 5.228 actually mean? It's simple. It tells us that a typical student in this class scored about 5.2 points away from the class average of 55. See? That gives us such a richer picture of the class than just knowing the average was 55.
But hang on, what about those outliers we talked about? Even the standard deviation can get pushed around by really extreme values. When we think our data might be a little messy, we have an even tougher, more robust method: the interquartile range.
To get the interquartile range, or what people call the IQR, we start with the median. You remember the median, right? It's the number that's sitting smack dab in the middle of your data once you line it all up. 50% of the data is below it, 50% is above it. We also call this Q2,
or the second quartile. Now, all we do is find the median of each of those halves. The median of the bottom half of the data is called the first quartile, or Q1. And you guessed it, the median of the top half is the third quartile, or Q3. And there you have it. Those 3 points, Q1, the median, and Q3, chop our entire dataset up into 4 perfectly equal chunks. Each one of those sections holds exactly 25% of our data. It's a really cool way to see the structure. So what's the interquartile range? It's just the distance between Q3 and Q1. Think of it this way. It's the range that holds the entire middle 50% of your data. It's the heartland of your dataset. And this is why the IQR is so awesome. Because it only looks at that middle 50%, it completely ignores the lowest 25% and the highest 25%. That means any crazy outliers at the very ends of your data have zero effect on it. It is incredibly tough and stable, which is perfect for messy, real-world data. All right, so let's put our whole toolkit together. You've got the range, which is great for a super quick glance. You've got the standard deviation, which gives you that classic, detailed picture of the average spread. And you've got the IQR, your go-to tough guy for when you think outliers might be trying to mess up your story. They're all different tools for different jobs. So I'll leave you with this. The next time you're reading an article or watching a report and they hit you with a big average number, what's the first question that's going to pop into your head? Hopefully it's something like, okay, that's nice, but what's the spread? Because now you know that is almost always where the real story's hiding.